So I'm going to start my presentation. Good morning. My dissertation is entitled BIM-based design validation for fire stations. My name is Ingrid, and my supervisor was José Granja, and the tutoring company was Gun Athletics. When we speak of design quality, we are usually speaking about a combination of effective solutions plus compliance requirements. And talking about those requirements, they can be building regulations, so they can be local codes, international building codes, accessibility standards, or it can be related to the design firm's goals. So sometimes the designers, they want to achieve a certain certification for sustainability, they want to apply for a financing program, usability, etc. And so these designers, they need to perform design checks to make sure that their buildings are compliant with the goals. And these design checks, they usually turn into time-consuming tasks, they cause rework, and they are also not very reliable. And this is the context that BIM can provide some effective solutions. When speaking about fire and emergency response facilities, these design checks, they are so significant because they can have a direct impact on the efficiency of operations and because they affect how firefighters are going to respond to emergency calls. And why did I decide to work with fire station design? So basically because of my personal experience, because I've been working alongside a company that is specialized in this building type. And also because after I started investigating, I noticed some lack of study in this area. So there are not much work relating BIM and fire station design. And also because I wanted to propose an advancement of fire station design practices. So my goals were to identify requirements and challenges faced during the development of fire stations, to define a set of critical factors that BIM model needs to include, to formulate an approach for automated room checking, and last, to implement the developed validation protocol on real-world fire station designs. Just to give you a summary about the literature review regarding automatic room checking, according to Eastman and other authors, when we speak about rule-based systems, there are mainly 4 steps. So the first one is rule interpretation, that is basically understanding and translating the rules into something that can be read by a machine. Secondly, we have building model preparation. So the designers need to prepare the models to be able to proceed the execution. And the third, rule execution. So basically in this phase, the engines are going to process the rules into the models. And last, we have report checking results. That is consists on presenting the outcomes of the checking process. So it can be shown as words such as pass, fails, some warnings, some diagrams, or other types of representations. In my work, I decided to implement visual programming language. So I'm going to call it here VPL. And some examples of VPL are Dynamo for Revit, Grasshopper for Rhino. And the good thing about VPL is that it's very user-friendly, so you don't have to have previous knowledge of coding to be able to work with VPL. And when we relate VPL and BIM, we can automate design tasks and processes that can be very repetitive if we are not using these algorithms. We can create parametric models, and we can create customized tools for specific project needs. So here we have the image of Dynamo Workspace. We can see that it's very visual. So we have the nodes and we can connect them, we can group, put colors and everything. And to speak briefly about fire station design, so fire and emergency stations, they need to avoid risks related to the firefighting tasks. They need to improve operational efficiency. They need to promote a healthy and sustainable environment. And according to MEON, there are mainly 4 functional areas that a fire station must include. So let's start with apparatus-based support and vehicle maintenance. That includes the contamination rooms and personal protective equipment storage rooms. We have the apparatus base, that is basically where the vehicle responses are going to be parked, the fire trucks, those big ones that we've seen it. We have the residential area, so this is the place that is sleep rooms, kitchens, fitness, toilets, lockers, they're going to be there. We have the admin area, so office, meeting rooms, workshops. And because I wanted to evaluate and propose an advancement in how the firefighters can travel within the emergency response facility, it was important for me to understand the components of response. So here we have the reaction to the alert. So the firefighters are going to receive the emergency call. They can be sleeping, they can be relaxing in their sleep rooms. Then they're going to travel within the fire station. So they're going from their sleep room to the apparatus bay. And then they're going to wear the protective equipment. And then they're going to enter the fire truck and declare response. So as I said, I'm going to focus in this travel within the fire station because this is the place that the designers can have a direct solution. They can have the major impact. And this time that is considered within this travel, we call it turnout time. So it's the time when the firefighter receives the call and is going to travel to the apparatus bay. And so how can we decrease the turnout time? We can place the apparatus bay strategically in a strategic place in the fire station. And we need to consider the horizontal and vertical foot travel distance. So how long is this distance that they're going to travel? And we need to consider horizontal obstacles. So for example, are there going to be too many 90-degree turns when they are traveling within the ERF? And when we speak about vertical obstacles, we need to consider if there are stairs, we need to consider sliding poles. So in this figure here, we can see a fire station that includes both a fire stairs and also a fire pole. And we need to consider the average walking speed because they cannot run, but they need to walk in an assertive way. My methodology, so I decided to work with design science research, the DSR, that consists basically on the creation of an artifact that can solve a real world problem. And the main idea is that I needed to build and evaluate this artifact. And in order to do that, I collaborated with Rice Fergus Miller, that is a US-based company. And the tools that I used to create this artifact was Revit and Dynamo. And also I needed to install some package for Dynamo. So the first step was to identify the rules. And to do that, I gathered with the principal architect and I received input from other designers. And also my experience working with the company. In this way, we could identify 10 rules that they needed to be verified for this design. And the idea was that these rules were going to be verified in the early stages of the process. So we have early design check and we have later design check, but they are both in the design development phase. And for my dissertation, I followed those 4 steps that I mentioned in the beginning, the 4 steps that Eastman listed. And to reinterpret the rules, which is to turn them into something that can be read by a machine, I applied RACE methodology that consists of creating markups into the requirements. And also I developed a pseudocode that this pseudocode helped me to develop my flow chart because with the flow chart, I was able to list the steps that I needed to execute the rule. And the flowchart helped me to create the Dynamo algorithms. So we can see here the workspace, and also I was grouping the nodes by colors to make sure that someone will be able to read it later. Then the next step was the model preparation. So I needed to create some families. Here we can see that, for example, I created this family for the fire pole that includes a hidden geometry for the to make it Revit read as a walkable path. Otherwise, Revit was going to read that this thing here was a hole and nobody could pass here. And also we can see that, for example, for the accessible toilets, they need to use a specific family, otherwise the turning radius could be not in the right place. I needed to include share parameters, view templates, views, and filters. And I applied these 10 rules into 3 case studies. I'm only going to show one more detailed. So this is a first fire station, is a ground floor fire station. First rule, we have the turnout time calculator. So this was the rule that was going to automatically create this path between 2 selected sleep rooms and the apparatus base. So this path here was created automatically. And we can see that it calculated the average distance, the average turnout time, and also includes information if this path is including fire pole or stairs. We can see here no path intersecting stairs, and we can see that both paths are walkable. We have the hallway maximum length. So in this case, this information here is showing by room number the maximum travel distance within each hallway. We have the accessible toilet clearance. So here we see the case that the turning radius here conflicted with the casework located in the toilet. We have hallway minimal clearance. So here we can see that the idea was to test if there is any dimension within a hallway that is shorter than 5 feet. Just a reminder that these projects are in imperial systems. So we tested including 5 feet, and we can see here that this dimension here was 4 feet and 10 inches. So the algorithm highlighted a red line showing that this dimension should be checked by the designer. We have the door clearance. So here we can see that it's conflict. The poolside area of the door is conflict with the lockers. And this tool here, the egress route analysis, we can see that the idea was that it was going to create an evacuation route from the furthest point in a room to the closest exit door. So the shortest route between each room. But the idea here is just to provide the designer with more information, because sometimes, although the shortest route is shown by the algorithm, is not actually the most logical route. So we can see here, for example, from this room, the shortest route indicates this exit door. But in an emergency situation in real life, the person is not going to do this. This person is going to take this path. So this is something that the designers need to evaluate as well. We have the fire rating check for the apparatus base walls and doors. And we can see here, for example, that we have 9 walls that we need to review the attachment, because if you have a wall that needs to be fire rated, it cannot leave a space between the wall and the roof. And we see that we need to revise the fire rating property in one of these doors. We have the fire rating check for the sleep rooms. So for example, here we have 4 walls that need to revise the attachment and 1 door. And this was the other 2 case studies. So this one has a huge area, two stories. This one is also 2 stories, a smaller area, but this one was very special for this study because it includes the fire pole. So for this third one, I selected 2 rooms in the upper level. And we can see that when the path was calculated, it considered the fire pole. So is in this place here. So if the firefighter needs to attend emergency, he's going to run and slide the fire pole to go to the apparatus bay, because this is the shortest distance. And we can see here, for example, turnout time includes fire pole. And then we have 19 seconds and 19 seconds. So the last step was the execution by a designated employee from the company. And also I provided this person with a feedback form and a manual of guidelines that this person needed to use. And this execution was really valuable for the research, because I was able to refine the tools, especially the guidelines, that there were things that the user was not able to perform because the person couldn't understand. And conclusions. So for the artifact development, I can say that we had some good application of the DSR method because we developed the artifact. And also we had a good implementation of VPL because we were able to create user-friendly tools in Dynamo. And then we had the user testing and feedback. So it highlighted the need for training, previous training before handling the guidelines and the algorithms to the users. And also it showed me that it needs a broader user testing because I only tested with one user, but we can test with multiple people within the company. And the feedback was really valuable, like I said, to refine the tools. Then we have for future development, I can see that this algorithm should be tested across various projects, so more than 10 fire stations. And I see potential application in other institutional designs. So I can see that this can be applied for schools, for example, or hospitals. And the impact, so I think that we had a demonstrated application of BIM in automating design validation for a specific building type. And I see here an opportunity to improve design and promote safety and efficiency in emergency response facilities. And those were all my references. So thank you.